is completely opaque to people who are not part of the respective transactions. To do that, I further complicate the structure of the coin. It has grown, and it now contains what we just saw before, this commitment to create a CM, and preliminary commitment to create K. There is a value V. But now there are other things going into this commitment. First, there's the address of the destination. Now, in order to have an address, you need to create one. So we introduce a new algorithm for creating addresses. The payee creates a public key and a secret key. They publish it, and in order to create a valid coin, I will need to have the payee's public key be part of the inner commitment. Moreover, the serial number no longer goes straight into that. And the reason for that is if the serial number was known to the payer, then the payer could cause damage. The payer could send the coin to the payee and then reveal the serial number before the payee had a chance to claim that coin, thereby invalidating the payment. To prevent that, we must somehow tweak things so the payer who sends the coin does not know the serial number of that coin. The way that's done is by making the serial number being generated by a pseudo-random function by the secret key of the payee. Pseudo-random function applied to what? Well, to some additional serial number randomness, and that is also made part of the commitment. So we still have the CM and SN, just like in the very simplest scheme, but there's a whole lot of internal values, randomness, commitments, keys, leading to them. And it does have just the right properties we need. Some of it can be readily verified. For example, minting is just as before. I reveal just enough values to make sure that I minted the correct V without revealing what I shouldn't. As for actually sending things so they can be used, now here's a bit tricky because we have two persons. The payer knows these secret values. The payee knows this value. None of them by themselves can compute all values, in particular the serial number. And that's actually as it should be. The payee should be able to claim a coin until he has received it. So there needs to be an explicit protocol for sending a coin to the payee. And that's done by creating a coin with the public address of the payee, and then sending all of these secret values, V, rho, R prime, R double prime, to the payee. And then the payee will have all of these values, also his own secret key, therefore he can compute the serial number, and then he knows everything, and he can produce zero knowledge proofs and spend coins analogously to what we had before introducing direct payments. Now, there's just a question of how do we send those secret values to the payee, and there are two options. You can either send them out of band. If you have their public key, just send it by whatever channel you have. Alternatively, as we described in the paper, we can bake in the public key machinery into the very currency, so that you will know where part of the address of the payee will contain the public key to which you can encrypt those secret values. If you know the payee's public key, you can send me the information, the payee can accept the coin. Okay, so now we've seen the basic structure of a coin, but we haven't seen how other things are done. How do we combine coins? How do we split coins? How do we crucially go back from ZeroCash coins into some mixture of ZeroCash coins and public coins, transaction fees, and so on? And all of these are captured by a single operation that we call the HOR operation. It's a single kind of transaction that provides a very general form that includes all of the specific operations I mentioned. And this general form is consuming two old ZeroCash coins, marking them invalid, creating two new ZeroCash coins with fresh serial numbers, fresh coin commitments, and so on. And also releasing some public value back into Bitcoin currency. Now, in order to create such a transaction, the holder of the two coins has to present his two fresh, unspent ZeroCash coins and the corresponding secret keys, specify how he wants this the value of those two coins to be split among the two new ZeroCash coins, and how much to be released into Bitcoin outputs, and moreover the addresses to which those fresh zero coins should be sent, which could be his own or someone else's. Now, the POR operation works for a while. This is the heavy part of the computation. It takes on the order of a minute on a modern desktop. And it outputs a proof attesting that the old coins were valid in the same sense that we had earlier by showing the knowledge of the internal values that fulfill those graphs we had before, which represent a predicate on the validity of coins. Moreover, those snarks capture the fact that the values of the old coins and equal the values of the new coins in total plus the public value. So, put otherwise, no new money was created. And moreover, it has to verify that the old coins were unspent to prevent double spending. In addition, there's a whole bunch of things outside this snark proof that go along, like the serial numbers of the old coins, the signatures on the destination of the public value if it's sent to some specific Bitcoin address and so forth. I'm afraid I won't have time to go into all these details. The paper is very explicit about them. I have to refer you there. Verifying this transaction, as you'd expect, verifies the zero-knowledge proofs and then checks the consistency of all the other values included in it. But you know what? Let me actually show you the transaction. I won't read out all of the details, but you can get a feel for what's going on, both qualitatively and quantitatively. So this is an example of in the content of an actual ZeroCash transaction. It's about 1 kilobyte in size. It includes the Merkle root capturing the set of all coins created so far. Here are the serial numbers of the coins that were consumed, the two old input coins. Here are the coin commitments of the newly created coins. You'll note that this public is value. Serial numbers are just some random value that we're seeing for the first time. These are just some outputs of commitments. So far, intuitively, we haven't revealed anything, right? Here we do reveal something. We reveal the public value. That is that the fraction of the input value from the two input ZeroCash coins that is revealed as Bitcoins. This reveals information, but of course this information has to be public. It makes it into the Bitcoin ledger. If the person who created the transaction didn't want it to be public, he wouldn't have made it so. So it's fine to have this information. Then we have some more random-looking information, but this actually is important. This is the destination of that public address, sorry, of that public value. The player here wants to send 42 satoshis to this Bitcoin address. So again, it's public, it reveals something, but by choice, we haven't violated anonymity. Then there's a bunch of strange things that are related to non-malleability. We won't get into that, but please believe me that they're all random looking and do not reveal anything about the transactions innards. These are two ciphertexts. If you use that option of having the caked-in public key infrastructure for sending those secret values needed to receive transactions, this is where you put them. If you don't want to use that option and have some external out-of-band channel, you can just drop these fields. And finally, the snark proof. So this is the actual the proof attesting to some fairly complicated statement about the validity of the altcoins. And as you can see, it's a few hundred bytes in size. So all of this, taking a step back, all of this is a specific scheme. It's the best scheme we could come up with, but it's an instance of a more general idea. And that general idea is that of decentralized anonymous payments. Decentralized anonymous payment systems, which are the way that we propose to formally capture the functionality that we require. So I'll be very informal about the algorithms that we use and who does what, and actually that reflects the attempt to show you the interesting bits without getting bogged down in formalities. But in the paper you can see a formal definition showing the algorithm setup that creates those public system parameters, the algorithm create address, the algorithm mint in its inputs and outputs, the algorithm pour and its many inputs and outputs, verify transaction, which does exactly what needs to be done in order to make sure that the mint or the pour transaction that appears in the ledger is legitimate by checking the snark proof and so on. And an algorithm receive, which is what inspects the ledger looking for transactions intended for me, and extracts the requisite values from them so I can use these coins. The definition of decentralized anonymous payment systems defines these algorithms and how to use them, and then defines as security. There are three security properties here. One is anonymity captured by ledger indistinguishability, which is a technical definition expressing the very powerful fact that nothing in the ledger reveals anything except for the public information. As I pointed out earlier in the transaction description. And this strong privacy property holds even against an adversary that can choose which transactions are to be done. They can manipulate parties into making any transactions that he wants. They can do transactions by himself, and yet he reveals nothing besides what is inevitable, just from the interface with the underlying currency, the public one. The balance property says that the monetary invariant is maintained. So no one can ever own more money than he received from others or minted from the underlying bitcoins by consuming them. And transaction non-malleability is a technical but important property saying that a man-in-the-middle attacker can intercept a transaction along its way to the ledger and corrupt it to change its value. For example, to have the public value sent to the attacker instead of its rightful destination. That, as you saw earlier, requires some extra machinery in the transaction. So we define this as the primitive, we described the scheme, and then we went ahead and instantiated and implemented it. We made concrete choices for all of the parameters and the underlying cryptographic primitives. We chose the best zero-knowledge snark available, and then we expressed our statement, the one to be proven by the snark, in the best way we could by speaking in the native language of the snarks, so to speak, which are roughly arithmetic circuits, and then hand coding the constraints, logical constraints required to check transactions in that low-level language. It was significant work, but it's part of the key to vast improvements in performance. Without this, if had we gone through the generic C compiler, things would have been orders of magnitude slower. Now this is all wrapped in ZeroCash, which is a library that creates the decentralized anonymous payments interface and abstracts away all of the underlying cryptography. And then we have Bitcoin de-adaptation that uses ZeroCash to actually integrate and interface this with the Bitcoin protocol, both in the sense of the protocol messages and in the sense of the monetary integration with the currency. To make sure that it indeed works and that the delays in verifying transactions and sending them are manageable and don't create any bottlenecks in the distributed ledger protocol, we actually went ahead and simulated the operation of a ZeroCash augmented Bitcoin system on a scale comparable to the whole of Bitcoin. So roughly a third of the Bitcoin, according to published estimates. We got a whole bunch of EC2 virtual machines, each running several simulated nodes. We ran it for a while, and